In this week's lab, we're going to be using the magnetic force to measure the permeability of free space mu naught. Now, in order to actually measure this, we're going to be using what's called an optical lever. And that optical lever is connected to two different wires. And of course, because I'm talking about the permeability of free space, I'm naturally talking about the magnetic force. And so really what we're going to be studying this week is the magnetic force that's created by one current carrying wire acting on another current carrying wire. So a sort of simplified version of our circuit is given in the diagram below. Here I'm going to imagine that wire 1, which is the bottom wire of our apparatus, is the wire that's going to be generating the magnetic field. So let's say we put the current through this bottom wire, which our lab manual calls I1, and I'll make it pointing to the right. Now, if my current is pointing to the right, by the right-hand rule, I'm going to expect that there's a magnetic field coming out of the board, or out of the page, or out of the video, or whatever you want to call it, above the wire, and a magnetic field going into the page, or the board, or the wire, or the screen below the wire, right? So if you picture yourself grabbing this lower wire with your right hand, that's the natural direction that your fingers are curling. And if I'm looking at the magnetic field above, right, because that's where wire 2 is, I know it's coming towards me, and I can calculate its magnitude if I know how far away it is, and that distance we're going to call r. The magnitude of the magnetic field at this point is going to be given by mu naught over 2 pi times the current in wire 1 divided by the distance r. Now, of course, this is idealized, right? This is the magnitude of the magnetic field if wire 1 is indeed infinite. Now, wire 1 isn't perfectly infinite, but you'll notice that wire 1 is actually a little bit longer than wire 2, and that's to make this magnetic field at wire 2 as constant and as uniform as possible. Now, if the current through wire 2 is pointing in the opposite direction, and that's going to be important here, right? Because if the current in the wire 2 is pointing in the opposite direction, pointing to the left, then the right-hand rule tells me that left cross with out is going to be up, and I know that my magnetic force is going to be pointed upward in wire 2. And that set of directions is really important to us because I want the magnetic force on wire 2 to be pointing upward, so that way I can counteract it by putting masses on wire 2 so that I can keep wire 2 in equilibrium. Now, your lab manual tells you that I know that the magnitude of this magnetic force, which I'm going to write as Fm, is equal to I2 times L times the magnitude of B, right, where L is the length of wire 2. I know that the magnitude of the magnetic force is I2LB. Your lab manual says to put this in your lab notebook. I don't think that that's strictly necessary because it's something that you covered in 240. So we have expressions now for the magnitude of this magnetic force. We've done the right-hand rule twice in order to get the direction of the magnetic force. And the magnitude of the magnetic force, of course, depends on the magnitude of the magnetic field, which is produced by the bottom wire. Now, my diagram looks a little bit messy, but we built it up together, so I hope it makes sense to us. Let's go through the logic just one more time. The current in the bottom wire is pointing to the right, right? That's what we call I1. The current in the top wire is pointing to the left. That's what we call I2. The current in the bottom wire is creating the magnetic field. Above that wire, the magnetic field is coming towards us. That magnetic field then produces a magnetic force on wire number 2. The direction of that magnetic force is upward, and the magnitude of that magnetic force is given by I2LB. Okay, and that's how we get the expression for that force, and then the rest of this is just algebra and plugging one equation into the other. Now, one of the tricky things is that this distance r that we're talking about isn't exactly something that we can read off the apparatus, right? Because when I have these two wires and I've blown them up here, the thickness of the wires is actually sort of comparable size to the distance between them. So the thing that we're calling R is actually the distance between the centers of the two wires, right? And that's the distance that we need from the symmetry of the problem that we use to get the magnitude of the magnetic field in 240. Now, I'm not actually going to be able to measure directly the distance between the two wires R. Instead, I'm going to have to measure two different distances. I'm going to have to measure the thickness of the wires, which is the thing that we call D. And I'm going to use calipers. We'll show you that I'll show you that in a couple of minutes. But we're going to use calipers to measure what the diameter of the wires D is. And we're going to use our optical lever to measure this distance here, which is the distance X. Right? So we have to reconstruct R by knowing what X is and by knowing what D is. And it's kind of convenient that the middle of the wire is half a D from the top wire and half a D from the bottom wire, so that R is in fact just equal to X plus, well, D over 2 plus D over 2, which is just equal to D. Okay? Now let's take a look at the experimental setup. So this week when you get to lab, you should see a setup that looks something like this. Now, this piece of equipment over here is the actual optical lever. And you can see there's lots of parts to it, and we'll go over that in a second. And then, of course, this is a power supply and a digital multimeter. This week, we're not going to be using the digital multimeter to measure potential differences. We're going to be using the digital multimeter to measure current. And therefore, instead of connecting one wire to the COM and one wire to this terminal on the digital multimeter, we're going to be connecting one wire to the COM and then one wire to the 10 amp current slot. The difference here is that when we use this as an ammeter to measure current, all of the current is going to flow into the multimeter in one of these terminals. It's going to flow out of the multimeter in another terminal. So it's going to be measuring the current through the multimeter itself. Do not connect this to either the V or the 300 milliamp part, because we're going to be using a lot of current today, right? So our current is going to be between 1 and 8 amps, and that actually is a lot of current. And so plugging this into the wrong terminal here will actually probably cause the digital multimeter to get damaged. So don't do that, okay? Now when you turn this on, you're going to put it all the way over to the A with the line above it, and that's going to be able to measure a DC current, and that's generally the first thing I do just so that I can have it ready for me when I'm ready to do the experiment. So our logic, or our flow of current, is going to look something like this. Our power supply has a DC out on the right-hand side. We've used this before. If I follow the wires, the red wire, or the high potential side of my power supply, is connected to my digital multimeter. That's going to be able to read the current. The current then flows out of there and flows through this little device here, which is, of course, the fuse. This is an incredibly important piece of this apparatus, this fuse, because we, after all, are dealing with a lot of current. And if we happen to short something out, or if we happen to drive too much current through here, we need something in the circuit to give before we actually start an electrical fire. So this fuse here is an extremely important place, is an extremely important part of doing the experiment today. I won't say that I've never taught this lab where somebody didn't blow a fuse, but somebody always blows a fuse when I teach this lab. Anyway, so let's put this thing back together. So we were following the current, high potential there, goes through the fuse, and then it enters this apparatus. And I need to make sure before I turn anything on that this wire is hooked up to the apparatus in a way that makes sense. So as I'm following the flow of current, this wire goes in here, goes down and across the top wire, back to the back, leaves through this, what's in this apparatus, a blue wire, comes around to the front, and then goes across the bottom wire in the opposite direction, right? And the fact that it goes through the top wire one way and through the bottom wire in the opposite direction lets me know that I have this setup oriented correctly, so that way the magnetic force that I'm measuring is going to be in the correct direction, right? That the magnetic force is going to want to take this top wire and move it upward. Once the current leaves there, it goes through this orange wire and back to the low potential side of my power supply. So as it's set up right now, everything looks pretty good. I have my ammeter connected in series here so that the current flows through it. It's connected to the 10 amp side so that way I don't blow it out. The current is flowing through the wires in opposite directions here. And now I seem to have something that's set up pretty well. So the idea behind this lab, or when I'm actually taking my data, what I'm going to be doing is I'm going to be turning on my power supply and turning up the current so that I'm able to adjust the total amount of current that's flowing through the system. Now, when I'm doing my data, I'm going to, that current is going to create a magnetic force. That magnetic force is going to push up on this top wire here. In order to measure that, I'm going to take these tiny little masses, which are in this nice little tan container, and I'm going to place those masses carefully on this little platform here in order to counteract that magnetic force and put the level back to where it was for my first measurement. So when I'm actually taking my data, I'm not going to be using the laser level to measure a height difference. I'm going to be using my laser level to just keep the top wire at exactly the same location, right? This thing R that we talked about earlier in the video is something that's going to remain a constant during my data taking time. In a moment, I'll talk to you about how we measure that, but this R is going to remain a constant. So as I change the current, I'm going to need to add more masses in order to keep R to be exactly the same, right? And that's the set of data that I'm going to end up needing. I'm going to need a current value and a force value so that I can make my plot. Okay, and these are the little masses that we're going to use in order to make those force measurements. Other measurements that you're going to have to take during this lab are, of course, a measurement of that distance between the two wires, which in the lab manual we call X. Now, I encourage you to look at the diagram in the lab manual very carefully because I think it does a nice job at explaining how we're going to use geometry in order to measure the distance the distance between these two wires. Now, each station comes with a little diode laser that's on a nice little pivot, and all sorts of things that you can put inside of here, so that you can have it at a permanent pivot. The laser is going to go the light is going to leave the laser, bounce off this little mirror, and then go quite a far distance and have put a little spot on the board or on the wall. And the idea behind using that laser to measure distances rather than trying to measure them by looking at the wires here are, one, I don't actually have to touch the wires to make a measurement, right? When I'm running the current through the wires, I don't have to I don't have to put a caliper or anything up against them. But any small difference in the distance between the wires is going to now be magnified by the lever arm. It's going to be magnified by a factor that's proportional to how far away the wall is or how far away the board is. And so if I take this and I look at the geometry that we've mapped out in the lab manual, if I take the equilibrium position, which is of course where all of my data is going to come from, and then I take these two wires and, again, without the power supply on, push them together, I can see how far that dot moved on the wall, right? And if I watch how far that dot moved on the wall, I can use trigonometry to find out the distance between these two wires. And that's something that I would do first, right? Get this level, right? As this rocks back and forth, and there are all sorts of masses that you can move around so that the wire is balanced right above the top wire is balanced right above the lower wire. Wait for it to equilibrate. Set up my laser level and see the point on the wall. And then once I have this as my setup, I can very carefully push this down, mark where the second point is, and then let it go back to its equilibrium position. And once I have that measurement of the distance that the dot moves, and hence be able to calculate the distance between these two wires, I really want to minimize my interaction with the actual physical setup, right? I don't want to jostle it. If you hit this too hard and one of these pivot points moves by a little bit, that's going to have a dramatic effect on the rest of the data that you're taking, because our resulting measurement depends so much on both being able to measure this value of x, but also being able to keep that value of x constant throughout my data taking run. The last couple of measurements that we're going to want to take is, one, a measurement of the distance of the length of this wire, right? Because the magnitude of the magnetic force depends on the length of the segment of wire. And we're also going to want to take a measurement of the diameter of this wire. And for that, we're going to use one of these mini calipers. These are a lot nicer than most calipers, because, one, they're digital, right? So they've already been calibrated. And when you turn it on, there are two different ways to tune it. There's a large wheel here that's a coarse adjustment, and then there's a way to hold on to the edge to do a fine adjustment. So there's the reading on the front then really just automatically reads off the distance between these two plates here. And it's an extremely precise measurement, right? So it's measured in millimeters, as I have it here, and it goes out to 3 decimal places in millimeters. So it's quite a nice tool for being able to measure things that are small. The other thing that I do want to mention is that with these tiny masses, please be very careful with them. They're calibrated extremely well, especially the smaller ones here are fractions of a milligram, or milligrams, I should say, not fractions of a milligram. But we don't want to lose these because even some of the sets I'm guessing probably have pieces missing. They can run off pretty quickly. And always use the tweezers, because oils on our hands and such can actually start to become important when I'm talking about measuring milligrams. And so just be careful with those. Okay, that's the setup. Remember, also don't turn this on until you've checked that the current knob is all the way down to 0, and then turn that on and turn the current up slowly. Once it gets up to a couple of amps, you really have to be careful with the setup. All right, don't put your fingers on it. Connecting that circuit could give you quite a shock, if not a nasty little burn on your fingers. If you were extremely creative and held it the wrong way and put that much current through a section of your hand or something, that actually would be rather painful. So please don't do it. Be careful with the apparatus when you have the power supply turned on. Well, be careful with the apparatus always, but especially when for your own safety when the power supply is turned on. So there are a couple of things that I want you to keep in mind while you're doing this lab. First, when you're taking the data, the key is, of course, to keep the wire wire 2 at exactly the same level. So that means that when the magnetic force is pulling up, you're exactly canceling that magnetic force with the gravitational force provided by the masses that you're putting on the wire. Okay? And that means that the laser dot on the wall should always be in the same spot. Now, this means coming up with pairs of data, right? The mass that you're putting on the wire compared to the current that's flowing through the wires. But you don't have to do these in exact increments of mass, right? You have a lot more control over the level of the current flowing through the wire than you do have on the amount of mass. And of course, as you're doing this, you want to place the masses very carefully on the wire, because you don't want the two wires to touch while you're conducting the experiment. And then only at the end, once you've disconnected or at least turned off the power supply, do you want to use the optical lever in order to actually measure that distance x between the two wires so that you can reconstruct what the distance r is. Okay, so at the end of the day, this basically amounts to just balancing forces, right? Magnetic force up versus gravitational force down. You just have to do it in a careful way, and then you can use that expression to calculate what mu naught is. Good luck.